So I'd like to take this moment to wish you all a very good morning. So about 2 of you are also having a good morning, and the rest of you are still sleeping, perhaps. That's all right. We'll wake you up quickly. My name is Dillon. I'm your instructor for the morning. I work for a company called Nthought. Also with us in the room today is my esteemed colleague, Alex, there in the back corner. He will be here to help answer your questions, especially during the parts of the class where you'll be working on exercises. Now, Alex has also been responsible for putting together this whole tutorial session. So could I see by a show of hands how many of us have learned something amazing so far? All right, can we get a round of applause for Alex and the hard work he's done? So we're here this morning to talk about NumPy, and this is going to be a big Indian talk, so we're going to put the most significant parts first. The very first thing that I would like to do is pull up the code of conduct for this conference, which you'll see at the very memorable endpoint ehome/220975/493 434. If you haven't looked at this already, I highly recommend that you do so. This is something that we take very, very seriously about making this a place that is amenable to productive scientific discourse. I would like to go a step further than that and say that if at any point during this conference you do not feel as if you are enthusiastically welcomed here, I would like you to come talk to me. If I make you uncomfortable, you can talk to Alex or any one of the conference organizers. If bringing this up with someone in person makes you feel uncomfortable, you can message one of the conference organizers on Slack to let them know what's happened. And it says all of the usual things about being kind to people, all the things about making sure you are taking other people's perspectives into mind, not making careless jokes or careless comments. So I think that is the most important thing. The next important thing is before we can talk about NumPy, we're going to talk about how we're going to talk about NumPy. So the general structure for this morning session is going to look like this. I will talk for a little bit. I will alternate between doing some doodling on the whiteboard here and some typing on my computer. And for the part where you see me entering code, I encourage you very, very strongly to type along. One of the things that we know is that the absolute worst possible way for you to learn this content is to hear me talk about it. So we're going to minimize these parts of the tutorial as much as we possibly can. I'm going to give you the least possible amount of information to make you successful in working on the exercises that we're going to have you spend time on. Now, these exercises themselves will come in two flavors. The first will be little practice things that I'll put here on the slide. It'll say create an array that looks like this, do this thing with it, then do this thing with it. The other exercises are going to be a little more involved. They're going to require that you open up a Python program. You're going to make some edits to it and look at the result to achieve some number of steps, some number of goals. When we get to this part, I will give you a brief introduction to those exercises, and we will let you fly to work on them on your own. We will circulate around the room to answer any questions that you might have. One more additional piece of information that's very important is the coffee disappears at 10:30, so we will be taking a break sometime before then to make sure you all have a chance to recaffeinate. So for this class, I am going to be using Canopy. It's going to give me all the things I need to show you NumPy and none of the things that I don't need. If you are working in the terminal, that's fine. If you're working in a notebook, that's fine. There will be minor differences in syntax between them. I will try to highlight those when we get to them. One of the chief ones is that during these exercises, there are going to be a lot of bonus components where you are asked to plot an array that you have created. And to make the plotting work correctly inside of an interactive session, like an IPython terminal we see here, we are going to enter some IPython magic matplotlib. If you are in a notebook and not in an IPython session, you want to follow this up with the word inline, I-N-L-I-N-E, like so. And if at any point I am talking too fast or drawing too fast or typing too fast, please do let me know. If there's a word I use that you haven't heard before, raise your hand and ask me to define it for you. If I use a word that you have heard, but I'm not using it in the way that you know it, you should also ask me as well. And if you feel uncomfortable raising your hand, I see that some of you have the little pink sticky notes from the software crappergy sessions. You can use those as well. So we're here today to talk about a library called NumPy. NumPy is a library inside of the Python ecosystem, and it's going to solve a very big problem for us. So we like working in Python. Python's an amazing language. It makes it very easy to do common things. It makes it possible to do uncommon things. It's clean to write. It's easy to read and understand. It's relatively easy to debug, and it's safe as a programming language. It does all of these amazing things under the hood for us to make sure we're not doing things like corrupting our computer. But Python has one major weakness. Python is not particularly good at math. Now, the way that we're going to get around this weakness is with using the NumPy library. And the very first thing that we're going to do is we're going to show you what this looks like. So what I would like to do is generate two ranges of data. One is going to be in a native Python data structure. And all we're going to do is calculate the sum of that data. We're going to do the same thing with a NumPy array. So we're going to generate a NumPy array of data, find the sum of that. And what we're going to see is we're going to time how long it takes each of those processes to complete. So to start with, I can make something like a test list. And this test list is going to be something that has, we'll say, we'll just do 1,000 integers. So the range function in Python is a built-in that's going to generate a list of integers from 0 to 999. You'll notice I've wrapped this in a list coercion. So if you are using Python 3, the range function has lazy behavior. So to make sure that we get an actual data structure out of this, we're going to coerce it into being evaluated eagerly by using our list constructor. Now the next thing we're going to do is we're going to create our NumPy array that has the same number of elements in it. So the first thing that we're going to do is we have to import that NumPy library. It's spelled N-U-M-P-Y. And you'll see I've used my alias importing here, so I'm importing it as another name. Now this is not a law in the world of Python, but it is a very strong convention. When you look at other people's code, you will almost always see NumPy imported under the name NP. Now this makes it easy, following the convention, for you or for anyone else. If they're looking at some function inside of a Python module and they see that NP name in there, we know immediately what that is. So I've imported my NumPy library. I'm going to use the NumPy, the concomitant function to range, which is called arange. And once again, we're going to make an object that has 1,000 elements in it. And now what we want to do is we want to take the summation of both of these data structures, and we're going to time how long it takes using IPython's magic time it. So in the world of IPython, we have a whole suite of really nifty functions that start with this %sign. We call these magic functions. The one that we want to use here is magic time it. That's spelled T-I-M-E-I-T. And we are going to time how long it takes to call Python's built-in summation function on test list, which is a Python native data structure. Python is going to run this function, this expression, a whole bunch of times, and it's going to give me its best guess as to how long this takes to execute, ignoring all of the other stuff my computer is doing, like talking to the projector, like running PowerPoint in the background. So IPython's best guess for how long this takes for my computer, it looks like is about 5 microseconds. On your computer, the timing might be different, and that's okay. Now we're going to do the same thing, but instead of using the Python function on the Python data structure, we're going to use NumPy's function on our NumPy data structure. So once again, we will have our magic time it. We're going to use np.sum, which is NumPy's summation function, and we're going to do this on our test array. Now, just like before, IPython is going to run this a whole bunch of times for us. It's going to give us its best guess for how long this is going to take. So for our small data structure that has 1,000 elements, what we see is that using NumPy makes this code run about twice as fast. This difference is going to get larger as we increase the size of our data structures. So for an array that has 1,000,000 elements in it, what we're going to see is that using NumPy is going to be 1 to 2 orders of magnitude faster. So somewhere between 10 times faster and 100 times faster. To give this a little bit of context, this is the difference between waiting a second for something to complete and waiting several minutes.
Can you comment on why that is?
That's exactly what we're going to talk about. Yes?
Is that just true for integer arithmetic?
So the question was, is the speed, this performance gain, only true for integer arithmetic? And the answer is that it is true for any kind of mathematical operation you'll be doing. The NumPy versions are always going to be faster than the Python versions. Now there are 2 primary reasons for this. And to explain why, I'm going to start drawing some pictures on the board. The first thing that we're going to see is we're going to draw out what a list looks like to Python. And we're going to talk about how we grab items out of that list. And then we're going to draw what a data structure looks like in NumPy and how Python pulls data out of NumPy arrays. This is going to involve me walking away from the microphone, so I will raise my voice so that you can hear me better. It's not because I'm upset by drawing. So if we think about the way that memory looks in our computer, in a Python list, we're going to have some array where that array is dynamically resized, and that array consists of pointers. Now, each one of these pointers you can think of as an address that knows where the objects inside of that array live. So this one right here, for example, might look somewhere else in memory where I have the string Dillon. This one here might be looking somewhere else in memory that contains another array, another Python list. And what this means is that when I go to retrieve one item, if that item is something like an integer or a floating point number or a string, every time I do this, I am adding one lookup. I have to go somewhere else in memory to fetch a thing. If I have nesting in my data structures, I might have 2 lookups I have to perform, I might have 3. Now, the time for any one of these individual acts is very, very small. We're talking on the scale of dozens of nanoseconds, so it's very fast if it happens once. But typically, when we're constructing NumPy arrays, it's not just because we want to add 1 and 2 together, it's because we have millions of elements that we need to summate, to take the standard deviation of, to find out where the maximum value is. And adding 40 or 60 nanoseconds to each one of those binary operations between elements becomes very large. So this isn't just 20 nanoseconds when you're doing it for millions and millions of things. We're on the scale of seconds now. Human noticeable slowdowns. Now for a NumPy array, instead of having references to references to references, what we have in memory is an unresized, dense array that actually contains inside of it the data that we're interested in. So there is no double lookup, there is no triple lookup. If I want the 1, I go to where I know the 1 is, and that's where my data is to. So this is one source of our speed improvement. The bulk of it, though, comes from the fact that Python is what we call a dynamically typed language. Now what this means is that we don't have to let the Python interpreter know in advance what kind of data we're giving it. Is this going to be a list? Is it going to be a dictionary? Is it an integer? Is it a floating point number? Now this makes it very nice for us when we write code in Python, because we can get rid of a lot of the boilerplate. We can write code that's more easily composable, more easily extendable. The downside is, if I have a simple operation in Python, where, for example, I want to take the sum of the number 0 and the number 1, there are a lot of intermediate translation and checking steps that occur. So when Python sees the 0 plus 1, the first thing it's doing is it's translating that plus operator to a dunder add method on that integer. And then it has a lot of checks. So for example, does the dunder add method of an integer here work with whatever is given as an argument to this method call? I have to check if this number is large enough that I have to put it in a different kind of data structure and a larger amount of memory. I have to check if there is an explicit, not implemented statement on the left-hand side of this operation, so that I can go and check on the right-hand side. And again, each one of these error checking steps, each one of these layers of misdirection, only adds a tiny fraction of time. But if you give Python a list of objects, it has no way of knowing if every object in that list is going to be an integer, or even if it's going to be a number. So it has to perform all of these checks every single time. So again, if we do it once, it's not a big deal. If we have to do this a million times, this adds substantially to the runtime of our programs. Now in contrast, when we create arrays in NumPy, arrays of numerical data, we tell NumPy in advance, these are going to be very specifically 64-bit integers. These are going to be 32-bit floating point numbers. These are going to be 128-bit complex numbers. So that when NumPy goes to perform our addition, it doesn't have to do these type checks on every single object in this array. It knows for every single one of these, I am always doing 64-bit integer addition. And it's going to perform all of these operations for us at the level of the code written in C, not written in pure Python. So not only are we avoiding all of these type checks, we're going to avoid also a lot of the overhead that we get from the Python interpreter itself.
But at some point you must make a check, right? You only make it once.
Exactly, you only make it once.
Because let's say you're reading a data file and it has an error as opposed to a number, it has a string, and you try to load it into a NumPy array, will it give you an error?
So the question was, if I am reading some data in off of disk and it contains something that is not representable as a number, do I have to check while I'm doing the addition for that? And the answer is you will see that error at read time. So if you read in data off of disk and you tell NumPy this is only going to consist of 64-bit floating point numbers, and there's some data in there that doesn't fit that format, you will see that exception immediately. So the benefit to using NumPy is we're going to be getting these 1 to 2 orders of magnitude performance gain. The cost that you're going to have to pay is we're going to move away from all of the nice protections that Python gives us. And what that means is that the numbers in NumPy are going to behave a little bit differently than the numbers that we're used to seeing inside of Python. We're also going to see that while the data structure itself supports many of the same methods we're used to using in Python lists, there are some restrictions to how we can use those. So an array looks a lot like a list, but there are some very important differences. In terms of the data structure itself, a Python list is allowed to be heterogeneous, by which I mean it contains data of different types. A Python list is also allowed to be resized. So one of the principal uses of a list inside of Python is to accumulate data inside of a loop. So you're generating data one by one, you append it onto the end of that list. Our NumPy arrays, in contrast, are required to be homogeneous in their data types. So if I have a two-dimensional array that I'm trying to use as some sort of a tabular data structure, I am required that every individual item inside of that table has the same data type. They can all be integers, they can all be floating point numbers, they can all be strings if I want, but they cannot be any mix of those things. The other principal difference is that a NumPy array is a fixed size. Now this is like 99% true. You can change the size of a NumPy array, but this is a very expensive operation.
Python always have a array.
I'm sorry?
Does the Python also have its own array?
I'm missing the second word. Does a...
The Python has its own array.
There is an array module in Python that you can import and use the array data structure. That is not the same thing as a NumPy array. So we've seen here that the data structure itself is going to be different in some key ways, but the data inside the data structure are also going to change. And to show you what this looks like, we're going to have to create a handful of NumPy arrays so that we can see in real time how they're working differently. So the very first thing that I would like to do is I would like to create an array. We're going to make an array of integers. And I'm going to use the constructor function for arrays inside of NumPy to do this, and we will give it a very bland and boring name like the letter A. So here's my name. I have my assignment operator. Yes?
Could you just scroll up just a little bit?
Oh, of course. So I have my name A, I have my assignment operator, and on the right-hand side, we're going to ask for a NumPy array. So np.array with an open and a closed parenthesis. Incline the open and the closed parenthesis, I'm going to initialize my array with some data. And here we'll have the integers -1, 0, 1, and 100. We're going to add one more thing, and I'll explain later what this is doing. We're going to use the optional argument dtype to specify the data type we would like this array to have, and the dtype is going to be int8. So this is a string literal that tells NumPy I want an 8-bit integer. I can hit enter to execute this line of code, and then here is my NumPy array. And now my first question for you is, when we're working with numbers in Python, in base Python, what happens when I try to divide a number by 0?
Error?
That's exactly right. So I get what's called a zero division error. So if I say I want to divide 1 by 0, here is Python telling me this is something it's warning me against. This is probably not what I meant to do, so it's going to raise an exception as a way of letting me know. we're going to do the same thing where we divide a number by 0, but we're going to divide the data inside of our NumPy array A. So the name A, and then divided by, and then a 0. Do I see a 0 division error? I do get a warning, yes. But there's no exception that gets raised. And the result of this is a valid data structure. It is a NumPy array that is filled with zeros. Yes?
I get infinities.
You get infinities. I would bet that what you've done is you have created an array of floating point numbers instead of an array of integers. So, good instincts. Now we're going there next. So the reason for this is that when we're living inside of NumPy, we're no longer dealing with Python data types. These are not Python integers. These are the kinds of integers you have access to if you are writing this code yourself in C. And they behave according to the IEEE specifications for how numbers should behave, and not according to Python's ideas of not surprising you. So you might find this to be a surprising result, that a number divided by 0 is 0. But the dark cabal that controls numbers has decided this is how this works. Yes. So there's one more thing that we're going to do. If I asked you a question, like how do I take the square of a number in Python, what would you tell me?
Multiply by itself.
Yeah, I can multiply it by itself. That's one option. Or I can use my double splat operator to ask Python to square the number. So here what we're doing is we have the Python integer 100, and we are squaring it. And we get the result 10,000, which is not surprising to us. This is what we expect. And I can take this to any power. And this integer will get larger and larger and larger, up to some point, and I will scroll up again, up to some point where we see this little L at the end of the number. If you're on Python 3, this is elided, so you won't see the L anymore. But this is Python's way of letting us know that this integer is now too large to fit into the size that is default on our system. So for most of you, it'll be 64 bits. But in Python, we're allowed to have integers that are arbitrarily large. So as our integers get bigger, Python will allocate more and more memory to holding those values. So we don't have to worry about things like numbers doing weird tricks, integers surprisingly becoming negative. In NumPy, we are not protected from this. So if I take that array A and I square it, we see that -1 squared is 1, which is what I expect. 0 squared is 0. This is also what I expect. 1 squared is 1. We're still feeling good. And 100 squared is 16. Right? We remember this from our multiplication tables. 100 times 100 is 16. So what's happened here is I have told NumPy, when I created this array, that I only wanted to give 1 byte, 8 bits, to each one of these integers. And the number 10,000 cannot be represented inside of 8 bits. So when we hit the maximum extent of that number, we started back at the negative end and counted up, which here is 16. If you would like to Google this later, the technical name for what we've just witnessed is called integer overflow. So we are also not protected from this. Let's try something else a little different. So we've been dealing with integers, but NumPy also supports floating point numbers, so numbers like 4.5. They cannot be represented as these infinite precision integers. And what we're going to do is we're going to make ourselves an array of floating point numbers by coercing our integer array into a floating point array. We can give it the name B, and we're going to say that I want my array B to be that array A, and we're going to coerce it with a method called asType. A.astype And here we will make you a 32-bit floating point number. And I'm going to do this by supplying the string literal float32 float 32. So here is my floating point array B. And you'll notice that there are little periods after each number to let me know that I'm now dealing with floats. And when we take this array B and we do what we did to the integers, we divide them by 0, we're going to see something even more different. So we are still not getting a zero division error, but this time instead of ending up with an array of zeros, we have an array that has 2 infs, that stands for infinity, 1 negative inf, that's negative infinity, and this thing here in the middle, that's the letters NaN. This stands for not a number, and you can think about it as roughly corresponding to the meaning of something that is undefined. It is impossible for me to tell you what the result of 0 divided by 0 is, so I'm not going to try. You'll see inside of the scientific libraries in the world of Python, this special object, NaN, is often used to represent missingness inside of your data. So if I'm receiving some array where I don't have valid data for some of the values, those values will be coded as nans, as not a number. Not a number has a peculiar law around it. If we look at the nan object, which we can access from inside the NumPy namespace, np.nan, and we ask Python, is np.nan equivalent to, so using the double equal sign operator, itself? Python tells us that this is not true. Now the logic behind this is if something is undefined, if it's impossible to know what it is, there's no way to tell whether or not it's the same thing as some other thing. So equality comparisons against np.nan always return false. One of the consequences of this is that if you are used to working in a library where it's capable of filtering out missing data, selecting all the locations where the data is equivalent to missingness or np.nan, this will not work for you in NumPy. This will not work for you in the scientific Python ecosystem. So in practice, every library that you'll use has its own built-in helper function for finding nan values. In the world of NumPy, this is called isNan. So we can ask Python, is np.nan a nan? And this does return true.
So is the output in 18 the type? I mean, can you assign a value of a NumPy array to that output? I mean, are the infinite, the nans, and the other infinites the same type?
So the question was, in the output of 18, are those infinites and nans the same type of data? And the answer is yes. So that in NumPy, we are required that the data we put inside of an array be homogeneous. So that encoding of infinity, both positive and negative, and the encoding of nan are themselves defined in the specification for how you encode floating point numbers using only zeros and ones. Now because of this, you can never have an array of integers that has a nan value inside of it, because nan is specifically defined in the standard for floating point numbers and not in the standard for integers. Yeah, of course, good question. So we get amazing performance gains when we use NumPy for our numerical work inside of Python. The cost is that we have to start thinking hard about numbers, about the binary representation of numbers, and the way those numbers interact with each other. At this point, I'd like to pause, now that we have given you the scary doomsday. You have to think about C data types. to ask if there are any questions. Seeing none, the strategy we're going to take to talk about NumPy arrays is the first thing we're going to think about is our access pattern. So how are we putting data into those arrays? How are we getting data back out? Then we're going to spend some time thinking about how we perform operations on those arrays. And we're going to separate this into what we'll call mathematical operations and reducing operations, and we'll explain what that difference is later. After we talk about how to do useful things, we will go back into thinking about the actual structure of these arrays for really nice tricks that we can do with them. So we've seen that one of the easy ways to create arrays inside of NumPy is to use that array constructor. We've also seen that we can use a range to generate a sequence of integers in the same way that we can use a range in the world of Python. There are a number of other sort of convenience functions inside of the NumPy namespace for generating very common kinds of arrays. So for example, I might want to generate an array that is only zeros. And there's a function that does this called zeros. I might want to generate an array of ones. And there is a function that does this called np.ones. And I might want to generate an array that is filled with nothing. And I can do this with a function called np.empty. Now, if you ever use np.empty, and we will later today in this class, each of these constructor functions is going to take the size of the thing that I would like to create. So for example, I can ask for a 2x2 array. And you'll see that it's not quite empty. It's filled with a bunch of what is essentially gunk. This is whatever was left over in that memory address before it became my NumPy array.
Approximations to 0.
Close, yeah. But for us right now, let's keep working with that array A. And the first thing that we're going to talk about is, given that I have an array, how do I retrieve data back out of that array? Now, for those of us who are familiar with working with lists inside the world of Python, arrays are going to work very similarly. So they're going to support the getItem behavior. They're also going to support the slicing behavior, but there's going to be one key difference that we'll get to in a minute. So if you're used to grabbing individual items out of an array using the square bracket syntax, out of a list using the square bracket syntax, this also works on array. Just like lists in Python, arrays are zero indexed. So if I want the first item inside of my array, if I want that -1, I ask for the item in the 0th position. Now you'll notice what's being returned to me here is the scalar value, -1. I'm not being returned a NumPy array. So just like in Python, when I use my getItem syntax, I also destroy that data structure. So I'm not receiving the number -1 inside of a thing, I'm just receiving the number -1. Just like in Python, I'm allowed to use integers to count forward across the items in an array. I can also use negative integers to count backwards from the end of an array to the beginning. So if I want the last item inside of an array, which is a very common operation to perform, I ask for the value in the -1th position. And here is that 100 that we put at the end of our array. So in the same way that NumPy is going to support the getItem syntax from Python, it also supports the slicing syntax from Python. So if I want to grab the first 2 items out of my array, I can ask for that array A have my open and my closed square bracket, and I can slice from the 0th position up to, but not including, the 2th position. So just like in the world of Python, My slicing bounds are always inclusive at the lower end and always exclusive at the upper end. And just like in Python, when I use slicing, the objects that are returned back to me are in the same kind of data structure that originally contained them. So I'm not getting a list of the numbers -1 and 0. I'm not getting a tuple of the numbers -1 and 0. I'm receiving a NumPy array of length 2 with the data -1 and 0 in it. Just like in the world of Python, if I am slicing all the way from the beginning of a list, I can elide that first number. And just like in Python, I'm allowed to specify a step size for my slicing operations. So if I want to slice from the beginning of a list, from the beginning of an array, all the way to the end of an array, and only grab every other item, I can use the syntax inside the square brackets, : 2. Just like in the world of Python, I can take one of these getItem calls, so asking for the -1th item, and I can put it on the left-hand side of an assignment operator. And now instead of retrieving the data from that location, it's permitted to insert data into that location. So instead of getting that item, I am setting an item in that place. So let's say that we want to replace that value of 100 with something like 5. We can insert the integer 5 into that last position. And when I look at my array A, that 100 is gone, and the 5 is there instead. So this tells us that NumPy arrays, even though they are of fixed size, are mutable. They are changeable. I'm allowed to swap in data into my NumPy array. Now the next thing that I would like to do is I would like to make a 2-dimensional NumPy array. Now I could write out my nested lists inside of lists and use that inside of my array constructor to generate this data structure. What we're going to do is we're going to use a shorthand method that's going to involve less typing for everyone and a less chance of making a typo. We're going to make an array. We'll overwrite the B array with a 2-dimensional array that we're going to create first by calling aRange. So np.aRange. np.aRange is going to give us a 1-dimensional NumPy array of sequential integers, and we will have the integers from 0 to 11. So I give the number 12 into my aRange call. Now because np.aRange is returning a NumPy array, I can treat it as if it is already a NumPy array and immediately call a method of array objects where that method is called Reshape. And I'm going to reshape this 1-dimensional array into a 2-dimensional array whose shape is 4 by 3. And we will scroll you up. Now, when we have 2-dimensional arrays, it's going to be very, very tempting to refer to rows and columns inside of that array, especially if you are someone who is coming from a language like R or a language like MATLAB. I'm going to try very hard not to use either of those words. That mental model will not help you in NumPy. And the reason is that in NumPy we are allowed to have any dimension of arrays. So we can have a 3-dimensional array, a 4-dimensional array, a 12-dimensional array. And inside of multiple dimensions, the concept of a row or a column is not going to make much sense. So for example, if I have a one-dimensional array in NumPy, it is not the same thing as a column vector. It is not going to be a 4x1 array. It is just an array of length 4. And this is going to be important when we talk about performing operations between arrays later. So when I create an array of shape 4x3, what we see is that 4 is in the direction going up and down on my screen. The dimension of length 3 is going left to right. And this is verbally awkward, but this is how I will try to refer to these things, is the dimension of length 4 and the dimension of length 3. So if I have a list that is nested in Python, I have to chain together my square brackets to select first from the outermost container and then from successive inner containers. In the world of NumPy, I'm allowed to specify that information all in one go. And the syntax is going to look very similar to the syntax we used before, with the exception that they're all going to be in one set of square brackets with each getItem call and or each slicing call separated by commas. The order of the individual get items and set items is going to match the order of the shape tuple we use to create this data structure. So the first call we provide to either get item or slice is going to be in the dimension of length 4, and the second one is going to be the dimension of length 3. If you're ever working with an array and you've forgotten what shape it is or what order the numbers come in, you can always check the shape attribute of an array. We don't want A, we want B. So here is my array B. Its shape is a 4x3 array. So if I want to get some data out of this array, maybe I would like to retrieve just the number 8. I have the name of my object B, followed by my open and my closed square brackets. I'm going to use my getItem syntax, where I'm supplying single integers. And we're going to count in each dimension where the data point we want is. So in the dimension of length 4, that 8 is in the 0th, 1th, 2th location. So I have a 2 followed by a comma. And in the dimension of length 3, it is in the 0th, 1th, 2th in that way as well. So I can ask for my array B at location 2, 2. And there's the value that I wanted, the 8. I can also supply slicing calls in 2 dimensions, so integers that include at least 1 colon. Yes?
Can you also do like the double brackets, like 2 in a bracket, a set of brackets, and then another 2 in a set of brackets instead of the comma?
Yes, we can. This will be better for a reason that we won't understand for like another hour or 2. So we can also slice in 2 dimensions. If, for example, I want the first 2 items in both the dimension of length 4 and also the dimension of length 3, I can change my 2, 2 to a colon 2, colon 2. And I will scroll up a little bit. And here are the first 2 locations in each one of those dimensions. When I was using that getItem syntax in 2 dimensions, I was reduced down to a single scalar value, so there was no containing data structure around me. When I am slicing in 2 dimensions, I maintain each one of those dimensions in my NumPy array. Now I can also mix and match getItem calls and slicing calls inside of these square brackets. So for example, I might decide that out of my array B, in the dimension of length 4, what I would like are the middle 2 locations. Sorry, that'll be 1 colon 3. But in the dimension of length 3, so in the one going from left to right, I only want the last one. So I'll use my -1 because I don't want to have to count upwards in my head. And we see that what gets returned to us is still a NumPy array, but it is a one-dimensional NumPy array. So in the world of NumPy, in my multi-dimensional arrays, anytime I use my getItem syntax, I collapse one of those dimensions. So what do you think I would do? What is a solution? If I wanted to retrieve just the 5 and the 8, but I would like my result still to be a two-dimensional data structure, a two-dimensional NumPy array. So I could use Reshape, that's true. In this particular instance, though, it's possible for me to do this in the call already, so I'm going to add one character to line 42, and it's going to return to us a two-dimensional NumPy array with the same data. Yes?
Do you use a colon to make that slicing index?
That's exactly right. So I can append a colon. So this is no longer getting the item out and collapsing that dimension. It is slicing the item out and maintaining that dimension, just preserving it. And now here is my two-dimensional NumPy array with the 5 and the 8.
Well, you're saying when you don't have the column, when you don't have colon, you're collapsing, is that the word you use, or you don't maintain its dimensionality?
That's exactly right. So the question is what I'm saying, that whenever I have a getItem call, so one of these integers that does not include any colons at all, is it always true that I'm collapsing one of those dimensions? And the answer is yes.
So how does it know where to move? For example, before you use -1 to call the last, but let's say you use -2. So how does it know if it moves in i's or j's? Or in the short dimension or the long dimension, the 4 over 3?
If I'm understanding your question correctly, you're asking me, how does NumPy know whether this -1 here is applying to the dimension of length 4 or the dimension of length 3? And the answer is that it knows by its position inside the square brackets. So I have two slicing calls now, separated by a comma. And what we can do is we can look at that shape attribute of B to see that the very first thing I supply to that slicing call, everything before the comma, corresponds to the dimension of length 4, because it's in the 0th position, they both are. Whereas the second slicing call, because it's in the 1th position, corresponds to the 1th position of my shape tuple.
So in 42, if you had used -1 at the end, you will get 8.
The question was in line 42, if I use -1 at the end, will I get the 8?
Sorry,
No. So if I use -2, I'm going to be stepping 2 things backwards. And maybe it'll help if we look at B again. So instead of slicing out the 5 and the 8 here, in the last position, I'm in the second to last position, slicing out the 4 and the 7.
Can you remind me what's the difference between the shape 2, 1 and the shape 2, only?
So the question was, what is the difference between a shape tuple that looks like this, 2, 1,
Yeah.
and a shape tuple that looks like this?
Yeah.
And the difference is that this tuple, the shape tuple, corresponds to a one-dimensional data structure. Now, because of the way the Python syntax works, I can't just have a 2 inside of parentheses. This is just a 2 with grouping parentheses around it. So the definition in the syntax for creating a tuple does not actually require the parentheses, but it requires is the comma. So a 2 followed by a comma is a tuple of length 1 that only has the 2 in it. So are you a MATLAB user?
I'm using that.
So if you're used to thinking about things in terms of column vectors and row vectors, the 2, 1 would be the column vector. But in this case, it's still a 2-dimensional data structure. So the next thing we're going to do is take this into, we're going to answer a question. Yes?
How do you get like the first item so that it doesn't collapse as well? Like you see like how you retrieve it by putting like the three brackets
Mm-hmm.
three and then comma and then colons. And you get the first item without it collapsing.
That's a terrific question. So the question was, if I have my array B, how do I get out just the first item instead of the last item? So what magic mix of integers and colons am I going to use to retrieve that data? So I will have my array B. And what I can do is in each direction, I can slice from the very beginning up to, but not including, the item in the 1th position. And so here is my 2-dimensional array that only has that very first value in it, that's 0. Yes?
If I got data and I don't even know how many columns and lines are there,
Mhm.
how do you find out? Like I get just data that nobody knows what's in there, and they tell me to find out.
Sure. So the question was, I often receive data and I have no idea what's in it. How do I find out how many columns and rows it has? And the answer is that you can use that shape tuple. So if you have not set this explicitly yourself, it's still a thing that exists. It's still an attribute that is defined on all NumPy arrays. And only if you're dealing with 2-dimensional data, only if you're unwilling to let go of the ideas of rows and columns, you can think about the first item as being the rows and the second item being the number of columns. But the very next thing we're going to do is turn this into a 3-dimensional NumPy array, where the idea of columns and rows maybe won't be so helpful. Yes?
Could I use that if like I was reading in a CSV file and I had like a header row that I didn't want in the array?
So the question was,
File, like header on each column.
yeah, yes. So the question was, if I am trying to read in data from a CSV, is there a way to do that into a NumPy array? The answer is yes. I'm not sure that we explicitly talk about it during the class, but you will use it in the exercises. So in NumPy, there is a Loadtxt function that will read data off of disk and turn it into a NumPy array. It's going to require that you specify some kind of file location. You should also, just to be safe, specify the data type you're reading in. But in addition, if I look at the documentation for the Loadtxt function, there's going to be an optional parameter called skip rows, which is right here. So if I know that I have one line in my file that's serving as those headers, I can skip that row entirely by setting skip rows to be 1. So the next thing that we're going to do is we're going to make a 3-dimensional NumPy array, and we're going to extract some data out of that. So we'll call this one C. And just like before, it's going to be the result of using the aRange function to generate a range of sequential integers. This time, you're going to ask for 24 integers. And the reason is that we are going to reshape this into a 3-dimensional NumPy array whose shape is 2 by 3 by 4. And if I look at my array C, we see that the dimension of length 4 on my screen is left to right. The dimension of length 2 is corresponding to, in the 0th position, this entire two-dimensional array, and in the 1th position, this entire two-dimensional array. That 3 in the middle is corresponding in the 0th position to both the line 0, 1, 2, 3 and the line 12, 13, 14, 15. So because screens are two-dimensional, these are displayed linearly one above the other, but mentally you can think about them being stacked like this. So now you and I together are going to grab some data out of this three-dimensional array. Now let's say that we want to extract just the number 17. So I want to end up with that scalar value. I don't want it inside of any kind of a data structure. And this tells you that I'm going to be supplying what kind of calls. Exactly right. I'll be supplying 3 getItem calls, 1 getItem for each dimension of my NumPy array. So we'll have my array C. We'll start out with our open and our closed square bracket. And the first thing I'm going to ask is the number 17 in the 0th position in the dimension of length 2, or is it in the 1th position in the dimension of length 2? 1, exactly right. So we'll have 1 followed by a comma. The next place I'm going to look is in the dimension of length 3. And is the 17 in the 0th, the 1th, or the 2th position in the dimension of length 3? Another 1. And now finally we have to look in the dimension of length 4. So is that 17 in the 0th, the 1th, the 2th, or the 3th location in the dimension of length 4? 1. There is my 17. Let's try something a little trickier. Let's say that what I would like to have is this entire two-dimensional array up here. So I would like to end up with a two-dimensional array of shape 3 by 4 containing the values 0 through 11. Since I'm starting off with a 3-dimensional array, this tells you that I will have exactly 1 getItem call and 2 slicing calls inside of my square brackets. So here is my C with my open and closed square bracket. And the question is, what is the first thing I put in? Is it a getItem or is it a slice? It is a getItem. That is exactly correct. And the reason is I want to collapse that dimension of length 2. So this will just be an integer followed by a comma. My next question is, what is that integer? 0, exactly right. Now, the next 2 things I'm going to put in, I know are going to be slicing calls. And what I'm going to use is I'm going to use the shorthand syntax to tell Python that I want to slice all the way from the beginning, all the way until the end. So I can have just bare colons separated by commas. And here is my two-dimensional array of shape 3 by 4. We'll do one more of these on our 3-dimensional array. So my last question here is, what can I do if I want to extract a 1-dimensional NumPy array containing the data from position 12 Sorry, from the value 12 to the value 15. And just like before, we'll start by asking, if I'm ending up with a one-dimensional array, and we're starting with a two-dimensional array, how many get item calls am I going to have? That's exactly right. I'm going to have 2 get item calls because I'm collapsing 2 dimensions. The dimension I'm going to be left with is the dimension of length 4. And what this tells me is that my get item calls are going to be supplied to the first 2 dimensions, the dimension of length 2 and the dimension of length 3. So I have my name C, I have my open and my closed square bracket. I know that the very last thing I supply is going to be the slicing operator. And now the question is, what are the first 2 things I put? So in the dimension of length 2 is the 12, 13, 14, 15 in the 0th or the 1th position. It's in the 1th position, exactly right. And in the dimension of length 3, is it in the 0th, the 1th, or the 2th position? 0. Very good. So here is that one-dimensional NumPy array with the 12, the 13, the 14, and the 15. Yes?
Can you do it without the colon, the slicing colon, and get this?
So I'm expected to supply a number of operators equal to the number of dimensions that I have.
Is there any way we can get from 8 to 15?
Is there any way that I can get from 8 to 15? Yes. How do you think I would do it?
First one would be 0 to 1, 0. Column 1. Because the 8 to 11, that's 2, the second row, and the 12 to 15 is first row.
Mm-hmm.
Should I put a parenthesis 2, 1?
So the answer is we're not going to be able to do it only using what we've learned so far. I think what I would do in this case is I would reshape it and then grab the data out that way. Do we have other questions?
How would you go about reshaping it just into a single dimension array so that all the numbers follow each other?
That's a good question. The easiest way is going to be using something like flatten or ravel.
What was the question?
Sorry, the question was, is there a way to take my 3-dimensional NumPy array and to make it a 1-dimensional array? Is there an easy way to do this? And the answer is that we have 2 ways of doing this. One is called flatten, one is called ravel. These are both methods defined on NumPy arrays. So if I have flattened this array first, it's going to be very easy to extract, what was it, the 8 through the 15?
Now you can do this.
Yes. Seeing no further questions, we're going to move into our first exercise of the day. This will be a slide-based exercise, and we're going to have you practice retrieving values from a 2-dimensional NumPy array. So I'm not going to make you work in 3 dimensions, at least not yet. Now, the very first thing you'll do is you will create this array, again by using that arange function, followed by reshaping it into a 5x5 array. And you're going to perform 3 separate data extractions. First, this is probably the easiest one. I would like you to extract the data that is outlined in yellow. The next thing that I would like you to do is to extract the data filled in with, I guess that's a red color. And the very last thing, and this will be the trickiest, is to extract those 4 values, the 5, the 7, the 15, and the 17, that are outlined in blue. Yes?
Since these are the same length both ways, how do you know which dimensions, which?
That's a good question. So in this case, you would have to know that the direction going up and down is in the 0th position in the shape tuple. So we have purposely been creating arrays that are not the same length in each dimension for this reason. So we've all been working on this exercise where we have a 2-dimensional NumPy array, and we have 3 ranges of data that we would like to get out of it. This thing at the bottom here that's outlined in yellow, these 2 things in the middle here that are filled in with red, and then these 4 data points that are outlined in blue. So we'll start with that first one, which is the 20, the 21, the 22, the 23, and the 24. And I would like you to tell me what combination of slicing and get item calls can I use to retrieve this range of data. A little louder, please.
4, colon.
Excellent. So in the direction going from the top to the bottom here, I want the item in the 4th position. So we're counting from 0, 1, 2, 3, 4. If I don't feel like counting all the way down from 4, I can also ask for the -1th, the last item in this location. In the direction going from left to right, I want all of these data. So I can supply that single colon to say I want to slice all the way from the beginning, all the way up until the end. So our next task was to grab 2 ranges of data, sort of in the middle. One was this 1, 6, 11, 16, and 21, and the other was the 3, 8, 13, 18, and 23. So what combination of get item and or slicing calls can I use to retrieve these values?
Colon, comma, 1, colon, 2.
So what we would like in the direction going from top to bottom is every single piece of data. So once again, we will use that bare colon. In the direction going from left to right, though, we don't want to retrieve all the data. We just want 2 of those individual items. We don't want anything in the 0th position. We do want the data in the 1th position, so I specify the 1. But now we have something a little tricky, because I don't want the data in the 2th position, but I do want the data in the 3rd position. So the way that I can get around this is I can specify a step size where I say I would like to skip every other item. So I can skip the 2 and also the 4 and only retrieve the 1 and the 3. We're going to use the same step size trick for the last example, which was retrieving the 5, the 7, the 15, and the 17. So what can I type? What combination of get item and slicing calls do I need to retrieve these values?
1, colon, 2. And then colon, 3, colon, 2.
Excellent. So in the direction going from the top of my screen to the bottom, we don't want anything in the 0th position, so we can start slicing from the 1th location. And by stepping with a size of 2, we skip the 10, 11, 12, and go right to the 15, 16, 17. In the direction moving from left to right, we again want to skip every other thing. So we're starting with the 0th data, so we do want the 5 and the 15. So we start at the beginning, and we do want to grab every other item because we want that 7. But here we're in a little bit of a bind because we also do not want the 9 and the 19, which is what I would get if I just used colon, colon 2 for the second slicing call. So what I can do is I can ask Python to slice up to the 0, 1, 2, 3th position, but not include the items in the 3rd position. So we are stopping our every other stepping at this point. Do we have questions about this exercise? So the reason that we start off retrieving data out of NumPy arrays using this combination of get item and slicing calls is that it is extraordinarily fast and efficient. And the reason is that unlike lists in Python, where I have nested data structures, the data from my NumPy array is all contained in one location. We'll look at how this works later, but given a combination that strictly consists of getItem and slicing calls, what I have is essentially random access to all of those data. And by random, what I mean is it's the same random in RAM for random access memory, as I calculate locations by performing 1 or 2 multiplication and addition steps. And I can go directly to where my data are, and I don't have to do any dereferencing or any searching. So I can look up all of the data using these 2 items, specifically just by a little bit of math. So this happens in constant time. So very fast and independent of the size of my array. However, it's relatively inflexible. So there are some ranges of data that I cannot retrieve, even if I have reshaping in the middle, strictly using combinations of slices and get items. So for that, we have a second way of retrieving data from NumPy arrays. And the second way is going to be using something that, for I don't know what reason, is called fancy indexing. There are 2 kinds of fancy indexing. One, where we are allowed to specify non-sequential integer locations of our data. And the second, where we are actually going to apply masks. And we'll talk about each of these in turn. So the first thing that I would like to do is regenerate our array A. So we can start thinking about this in 1 dimension first. So here is my array A, 1-dimensional of length 4. Now, if I want the very first item and the very last item, I could actually use a slicing call for this. But what I can do instead is inside of my square brackets, actually pass in a list of index locations for each of these. So I can retrieve the data in the 0th location and in the 1th location. Or the 0th, the 1th, and the 3th. Now the same practice applies to 2-dimensional data structures. So if we look at my array B, this was my 4x3 array. I can use my square brackets for retrieving data. But in this case, instead of passing in 1 list of individual integer locations, I'm required to pass in 2. 1 for each dimension. So we'll have the list for the direction going from top to bottom, and the list for the direction going from left to right. And the way that this is going to work is that inside of each list, I'm going to be specifying, across the 2 lists, I'm going to be specifying pairs that represent each position, each item I want, in this direction, and simultaneously in this direction. So for example, if one of the data points I want is the 2, this is in the 0th direction in the dimension of length 4, and in the 2th location in the dimension of length 3. If I would also like the 6th, this is in the 2th location in the dimension of length 4, and the 6 is in the 0th dimension, in the 0th location in the dimension of length 3. And here is my resulting array with a 2 and a 6. Now this also applies in 3 dimensions, where I will have 3 lists for my integers, and the location for each individual data point is going to be separated. You can think about it as being the x, the y, and the z coordinate across these 3 lists. So we can look at my array C. This here is my 2x3x4 array. And from my array C, I can give 3 sequential lists of integers, where let's say I want the 6 and the 17. So the 6 is in the 0th location in the dimension of length 2, the 1th location in the dimension of length 3, and the 2th location in the dimension of length 4. To get the 17, we go back to that first list and add in that it is in the 1th location in the dimension of length 2. It is also in the 1th location in the dimension of length 3. And finally, it is also in the 1th location in the dimension of length 4. And here's my resulting array of a 6 and a 17. Are we having fun? So this is very tedious to do by hand. Typically, you will not be typing in the numbers yourself, counting in each dimension like this. But you will see this is the output of some of NumPy's built-in functions. So if you ask, for example, where something is, you will get a result that looks like a list of lists like this, that you can supply into a getItem lookup call attached to an array in this fashion. By far, the more common method of fancy indexing is going to be creating a mask. Now, we haven't talked about mathematical operations on NumPy arrays yet. This will be the next big topic. But the mathematical operations we apply to an array are performed element-wise. So in turn, vectorized to each individual data point inside of my data structure. So if I ask for my NumPy array C, where those locations are greater than 16, what we'll get back is a NumPy array of the same size and shape, where instead of being filled with numbers, it's filled with Boolean values. The Boolean values will be false in all of the locations in my original array that are less than or equal to 16, and it will be true for all the locations in my array that are greater than 16. So the very first true value here is in the location of the 17 in my original data array. Now, given that the mask I generate is the same size and shape as another array, I can put this mask inside of square brackets as a way to retrieve just the data that are satisfying some particular condition. Yes?
Is that always going to be one-dimensional?
The return result, yes. So the fancy indexing are returning flattened arrays.
It's just generating a new array, but it doesn't change the C.
That's correct. So we are not performing any modifications to C. C is still all there. Now, there's one more thing that's going to make fancy indexing slower than doing our get items and our slices. And the reason has to do with the way that NumPy thinks about efficiency. So NumPy, when you use your combination of get items and slices, doesn't actually copy any data around in memory. So for example, if I take my array C and I slice some data out of it, so maybe we'll grab everything in the dimension of length 2, and I'll scroll this up a little bit, everything in the dimension of length 2, and I only want the, we'll just grab one piece of data in the dimension of length 3, and then the middle 2 in the dimension of length 4. We can assign a name to the output of this. We'll call you D. So here's my array D, a 3-dimensional NumPy array. But this is not actually its own separate data structure. So D is its own object, but we haven't moved any data around. If I want to be sure about this, on my IrateD, I have an attribute called the flags that contains a number of facts about the NumPy array that I've created. The one that we're interested in is the one right here, asking, does this array control its own data? And the answer is no. So my IrateD is a separate Python object, but it hasn't created any copies of the 5, the 6, the 17, and the 18. What it does is it holds references to the locations of those data inside of my original NumPy array. Now, this can be good for efficiency purposes because copying data in memory is a very expensive operation. For us here with our little 4 data points, this would be trivial. But if you're dealing with an NumPy array that has millions of elements in it, we're talking about serious savings both in computational time and in memory space. The risk is changes that I make to D are also going to be reflected in C. So for example, I can grab some item in D. We'll grab the 5 is in position 0, 0, 0. And we'll make you some large number like 1,000. And sorry, I will scroll up. When I look at my array D, we see that D has changed like we expected. Now when I look at my array C, we see that C has also changed. Now this makes it very easy to extract subarrays out of an array and manipulate them in place. So this might be exactly the behavior that you want, but if you don't know that it's there, this can be very surprising. In contrast, when I use fancy indexing, NumPy will try really hard not to copy data around, but there are some things that it cannot represent with just a view. So if I use my up arrow to get this line back from history, where we were grabbing everything out of C, where C was greater than 16, we can give this a name as well. We can call you E. And when we look at the flags of E, we see that when NumPy created this object, it also had to recopy all of that data to a new place in memory.
Sorry, when you say why is it now its own data? Why is E its own data?
So E is its own data in this case because we have used something called fancy indexing. So because we've used this Boolean mask. Now if we have time, we'll actually go over why this occurs towards the end of the tutorial. To give you a short introduction, in memory, my NumPy arrays are these contiguous data structures, but they're always one-dimensional. So in my computer, this is always laid out in just one single line. NumPy tricks your computer into treating this one-dimensional data structure as if it has multiple dimensions by specifying a set of numbers to say this is how many bytes you move to pretend that you're moving in 3 dimensions, in 4 dimensions, in 5 dimensions. So any recipe, any subset of data, and this is, if you want to look at this, this is the strides attribute. And we might have a chance to talk about what these numbers mean later. But any recipe, any subselection of data that I can represent by modifying the starting location of my array or the strides, I can represent very simply just by storing some mathematical formula somewhere in memory. And I don't have to move any data around. Yes?
If you were to reshape D when you sliced it out of C,
Mm-hmm.
would it then put it in memory?
If I were to reshape D when I sliced it out of C.
Like in the command where we said D equals
Mhm.
C and then sliced?
Oh, good question. So the question was if when I grabbed my array D out of array C, if I put a reshaping call, would this actually make a new copy of all this data? And the answer is no. So I can perform as many reshaping operations on D as I want, And we'll talk about this a little bit later, but we're not actually modifying any of the data, the actual array portion that exists in memory. So if I do reshape into like a 4x1, so the numbers 1,006, 17, and 18 aren't going anywhere. They're still in the same places. What I've done is I've changed just the number of attributes on my array. So in this case, I've changed the shape attribute and the strides attribute. And in this case, not the number of dimensions, although that sometimes happens too. So reshaping operations, transposing operations, you can transpose arrays in NumPy with the .t attribute. These are extraordinarily cheap operations because they modify just 2 or 3 integers that are being held in memory. So if something like a reshaping call or a transposing call makes it easy for you to do the kinds of calculations you need, you can fearlessly apply these everywhere you want. It's going to cost you almost nothing. Yes?
What was the C on data flag prior to the creation of D?
What was the C own data
D,
flag?
does it go, when we create the D, does it go and change the C own data?
Oh, so this is a good question. What you're going to see is not what you expect, and I'll explain why. So C was a 3-dimensional array that we created using the A range in the reshape call, and we would expect, since it's a very new thing that we've just made, that it would own its own data. When we look at the own data attribute, it's set to false, and the explanation is this. When we created the array, that creation step happened in the A range, and it's that A-ranged object that owns the data. We've reshaped it, and we've stored a reference to the reshaped version. Now, we ourselves don't have a reference to the unreshaped data, but Python still does.
Okay. So it was there prior to D being created?
Exactly right. Yes?
So you mentioned the transpose function that you did with D, and I understand that for like a 2-dimensional array.
Mm-hmm.
When you did it on a 3-dimensional array here, how does that work? How's that defined? What's that doing? It looks like it left the first dimension alone and did a transpose using the last 2 dimensions?
Sure. So I would love to answer that question like right now, but I don't actually know how transposes work in multiple dimensions. So I'm used to thinking about them in 1 or 2 and not in like 12. What I can do is I can look up the actual implementation, and I'll get back to you with how they do it here.
Thanks.
Mm-hmm. So seeing no further questions, I have another exercise that I would like you to do. Just like before, yes?
Okay, so you said when we first started that D didn't own its own data. That was false.
Correct.
And now you're also saying, because D was derived from C,
Mhm.
now you're saying C itself doesn't own its own data either, because really the reshape, or no, the A range is the one that controls, that holds the data.
Correct.
So when you have multiple calls, like we said, B equal NP dot A range and C equal NP dot A range, are there 2 instances of the A range? One that holds what B is a copy of, and the other one that holds what C is a copy of?
So the question is, if I understand correctly, does the A range function itself own this data? Are there separate ones that are being created every time I use this reshape? That's not quite correct. So this is a little bit confusing, and I'll draw you a picture in a second. The short takeaway is that if own data is set to true, you are guaranteed that this array is the original owner of its NumPy array. If it's false, it might be accessible through another name. It might not be. So what's actually happening looks like this. When I have my initial call to that arange function, arange is creating a NumPy array. We were going to sort of save this to talk about it later, but we can talk about it now. The NumPy array itself has 2 components. It has some header that contains metadata, and this is where all those attributes are, like the .shape we looked at. There's a .ndim for the number of dimensions. And that header also contains a reference to where my actual array is. So this is where I would have my numbers like the floating point 1, the floating point 2, the floating point 3, the floating point 4. So arange produces this data structure. When I do my reshape call, that reshape is applied to this data structure. And what reshape is doing is it's creating just another header somewhere over here. And this header holds a reference to this original data, but its shape is going to be different. So maybe in this case, its shape is something like a 2 by 2. So this is the reason that our array C doesn't believe that it owns its own data. So even though we don't hold any reference through a name in Python to be able to access it, there is some object that exists somewhere that Python still has a reference to.
So what I asked was, we called it twice, so there would be two copies, two separate reference
Correct.
memory locations, so to speak. That
So every time I use a constructor function like array, a range, zeros, empty, I'm getting both a new header and a new array. When I'm doing calls like reshape or transpose, all I'm getting is the new header. When I'm doing fancy indexing using those lists of integers or a Boolean mask, NumPy will try really hard only to give me a new header, but typically it's going to have to copy the entire array as well, or the subset that I want.
So if A goes away, does it break the whole reference?
So the question was, is if there are no more references to this thing, this original combination from arange, does this object here stop working? And the answer is no. So Python's garbage collector, even if this disappears, Python's garbage collector can see that this array is still being referred to by something. So it's still being referred to by B or C or whatever we've decided to call this array. So in Python, humans are allowed to hold references to objects by giving them a name and the assignment operator, but objects also very frequently refer to each other. So this array here will stay in memory until every single reference to it has either been deleted or has gone out of scope. And then only then will the garbage collector come along and scrub it out. Talking a little bit about where data comes from, how arrays can own their own data or not own their own data. And this had sort of stemmed from a conversation that we were having about fancy indexing and when we would or would not want to use it. So the very next thing that I would like to have you do is to work on an exercise. This will be another short slide-based exercise where you will be using fancy indexing to retrieve some data. So once again, we're going to have a two-dimensional NumPy array. Once again, it will be 5 by 5. And I would like you to do two things for me. The first thing I would like you to do is to extract all of the values here that are filled in with the color blue. This is not something that you will be able to do using slicing. The second thing I would like you to do is to retrieve all of the data from this NumPy array where that data is divisible by divisible by 3. For this particular task, if you haven't used this before, I would recommend looking into the modulo operator. In Python, this is the %sign. We've all been working on this exercise where we have a two-dimensional 5 by 5 NumPy array. And we have two tasks that we would like to perform. We would like to use fancy indexing first to extract the range of values here that are highlighted in blue. And secondly, to extract all the numbers that are evenly divisible by 3. So in the first task, I want this off diagonal of the 1, the 7, the 13, and the 19. So in this case, what I would like to do is use the fancy indexing where I supply in each dimension individual integer locations for each one of these items. So since this is a two-dimensional data structure, I will have two lists of indices that I'm supplying. What am I going to put in my first list? 0, 1, 2, 3. Excellent. And what goes in the second list?
1, 2, 3, 4.
Exactly right. 1, 2, 3, 4. And there are the values from my off diagonal. If you didn't want to type out the integers by hand, you could have noticed that these are sequential integers and that I have built-in functions that will generate these for me. So we could use something like range instead. That's exactly right. For the second task, we wanted to discover and retrieve all of the data inside this array that is evenly divisible by 0. How can I do that?
A brackets, a mod 3, double equal sign, 0.
So maybe we'll break this down a little bit. The first thing we'll look at is that a modulo 3, so the modulo operator in Python is this %sign. The modulo is going to return the remainder after taking 3 out of each of these numbers as many times as it can be done. So we see this NumPy array here that's being returned to me of the same size and shape. That's filled with 0s, 1s, and 2s. For all those operations where, had I done my division, I would have nothing left over, versus I would have 1 left over, versus I would have 2 left over. So essentially what I have here is an array full of remainders. Now, to find out what's evenly divisible, the next thing that I have to do is find all of those locations where the values are strictly equivalent to 0. So I can use my double equal sign comparison operator, and now I have that Boolean mask of the same size and shape filled with true and false values, where the trues correspond to all of the locations where there is no remainder after dividing by 3, and the falses correspond to all those locations where there is a remainder. Now finally, I can wrap this in square brackets and use this to retrieve just those numbers which are divisible by 3. Do we have any questions about this exercise? Yes?
For the first one, can you also do a bracket x, x plus 1, that doesn't count as...
A bracket x?
A bracket x, comma, x plus 1.
Like this? I think you have an object that I don't. So depending on what A is, possibly.
I have it stored as the array from 0 to 3.
Then yes, in that case that would work. Seeing no further questions, I have another exercise for you. This is going to be a longer exercise that's contained in a Python file. So what I would like you to do right now is to navigate to the location where you have either downloaded or cloned the materials from the repository for this tutorial. Inside of that location, you have a PDF version of the slide exercises that you've seen me posting up here. You also have a folder called exercises. In that exercises folder is a sequence of subfolders. We won't have time to do all of these today, but they are there if you would like to do them for homework. And the first exercise that we are going to do is an exercise called DAO under selection. And the exercise itself is in the file called DAO under selection.py. In the DAO under selection.py file, you'll see at the very top, encoded as a module doc string, is an explanation of the exercise that you will be doing. Very briefly, in line 51, we're going to be using that NumPy Loadtxt function to bring in a NumPy array to our current session. And what you're going to do is you're going to retrieve subsections of the entire DAO dataset. So for example, one of the tasks you'll be performing is retrieving or finding the location of just those days when more than 5.5 billion shares of Dow stock were traded. So I will have you work on this exercise, and I will again do the thing where I wander around the room and answer questions. So we've all been working on this exercise, one of the longer exercises, where we have this file, dow_selection.py, where we're reading in some stock data and performing a couple of operations on it. So we are extracting data, counting that data, and then finding out where those data are. So what I've done here is I've loaded in that dow.csv file under the name Dow. Here is my Dow array. I can do something like check the shape of my Dow array, and it tells me that I have 168 observations, and I have 6 kinds of observations, where these observations correspond to things like the opening price, the closing price, the high price for each day. Now the first thing that I want to do is to create one of those Boolean masks that's going to tell me which days have trading volumes that are greater than this very large number of 5.5 billion. So how could I accomplish that? I'll give you a hint. I'm going to have to use the array Dow. Sure. So this is one option that I have. And instead of writing out all the zeros, I'm going to use a little bit of shorthand syntax. For those of you who haven't seen this before, in Python, you can use scientific notation as a floating point literal number. So this is giving me all these locations where my trading volume is greater than 5.5 times 10 to the 9th. What I would like is some sort of Boolean mask. So I can erase that outer container. And what I might do is I might think that I can use this comparison directly. So all the locations in Dow that are greater than 5.5 times 10 to the 9th. In this particular situation, though, it's returning to us a two-dimensional array with a true or false for each one of those individual elements inside the array. So it's telling me that none of my opening prices, for example, are greater than 5.5 billion, which would be very surprising. It's a very expensive stock. So what I would like to do is perform, this is the correct comparison, but I would like to perform it on a subset of the data. So what we can do is we can select all of my observations in the top to bottom direction, but only the data that represents the volumes. And if we look in here, we have a little helpful constant that's been defined for us that tells us that these are in the 4th location. So I can ask for the data in position 4, which is giving us only the trading volumes. And then I can ask where those are greater than 5.5 times 10 to the 9th. And here is my Boolean mask, where I have true values only for those locations where I have very high trading volumes. In the next question, it tells us to figure out how many days had a trading volume greater than 5.5 billion. And the hint is to use the summation function. So what I will do is I will use my up arrow to get this back. I will give you the name mask so I can do some stuff with you later. And now how can I use my mask and the summation function to tell me how many days had very high trading volumes? Exactly right. I can ask for the sum of that mask. And it tells me that I have 18 days. Now you'll notice, specifically I'm using the NumPy version of the summation function and not the Python version of sum. They'll both give you the same answer. But generally speaking, data structures that have methods defined on them in the same library are optimized to work well with each other. So we might have time to look at this later, but what we'll see is that NumPy summation function is much more efficient on NumPy arrays than Python summation function is. So we can save ourselves a little bit of time by using the concomitant NumPy sum function on a NumPy data structure. My very last task was to use a function called where inside of the NumPy namespace to give me the locations of all the days with very high trading volumes. So how can I use where to tell me which integer locations have very high trading volumes? So I can use np.where, and I can give it that Boolean mask, and this is giving me all of the locations in that mask that contain a true value.
Aren't we expecting like a two coordinates, so you need an X and a Y?
So our mask here is one-dimensional. It's reflecting the locations just in the top to bottom direction in the original array, not both the top to bottom and the left to right. If we had that left to right direction, in addition to this array that contains the 12, the 13, the 15, the 51, there would be another array that just contained 4, 4, 4, 4, 4, 4.
But this is what we were asked to provide, and not the 4 and
So I think it's just asking for the index, so the location in that top to bottom direction. Yeah. All right, do we have any questions about this exercise?
In the mask, it says have to specify what to return.
In the
Well function.
Mhm.
The help well function says have to specify the return value. So in the function you write here, there is only mask, but it seems that, or does it using default return?
So when you're looking at the function signature here for np.where, this x and the y here in the brackets, these are optional. So this isn't something that I'm required to pass in.
So why did you use put in as an argument where mask and not mask equals true?
So the question was, in np.where, why did I supply just the Boolean mask and not Boolean mask equivalence operator to true? I mean, the answer is that they reduce to the same thing. So if I ask for all the locations where true is true, it's going to return the same Boolean mask to me. So this is specific to the structure of this particular situation. But generally speaking in Python, every single object can be coerced into a string, and every single object can be coerced into a Boolean value. And it's very, we would call it idiomatic. So if you've been writing Python for a long time, you will see people not include the strict comparison to true. They will just use the object itself and let that coercion happen implicitly. So now that we've seen how we can extract data out of NumPy arrays in a very fast and efficient manner, what we would like to do next is to see how we can perform operations on those kinds of arrays. We're going to structure our idea of performing operations on NumPy arrays into sort of two different camps. One of these we will call mathematical operations, and the other one we will call reduction operations. A mathematical operation is going to return an array of the same size and shape. A reduction operation is going to return an array that's smaller. So when we say that it's a reduction, we mean we're reducing the amount of data that we end up having. So something like addition is going to be a mathematical operation. Something like taking the summation is going to be a reduction operation. Now, inside of the world of NumPy, when we perform any kind of mathematical operations between NumPy objects, we have to be very, very concerned about the shape of things. And what I mean by that is if we have some array like A, for example, here's my two-dimensional 5x5, I am allowed to do something like add a scalar to my array, where that scalar is added element-wise to each item in my individual array. I am also allowed to add an array of the same size and shape. So I can add a 5x5 array to a 5x5 array, and what I get back is a 5x5 array. But I cannot, for example, add together a 5x5 NumPy array with a length 7 NumPy array. And if we try this, what we see is that we get an exception from NumPy saying that the shapes don't fit. It doesn't know how to map a one-dimensional array of length 7 onto a two-dimensional 5x5. Now, in some languages, if one of those dimensions is evenly divisible by the other, the language itself will repeat the values from the smaller array. NumPy won't do that either. Now, the shapes that you'll need to perform these operations are going to vary depending on the kind of operation you're trying to do. So the way that they need to match up is going to be different for simple binary operations like this than it will be for something like the dot product of two matrices or the outer product of two matrices. But it's always something that you're going to have to worry about. For these kinds of operations, bless you, we've seen that a scalar value works, an array of the same size and shape works. I can also have arrays of two different shapes, provided they are capable of being broadcast together. The word broadcast here has a specific meaning in the world of NumPy. It means they follow a set of rules that will allow them to be fit together as if they were the same size and shape. So to see what this looks like, we can take our array A and we can try to add in a one-dimensional array of length 5. And what we see here is that even though these are not the same size and shape, they are capable of being combined. So when NumPy sees my attempt to combine this two-dimensional array with this one-dimensional array, the first thing that it's going to do is it's going to prepend a 1 in front of this 5, as many 1s as it takes to make these two arrays have the same number of dimensions. Any non-one length dimension, so here the dimension of length 5, has to match exactly. So the very last dimensions in both of these arrays are of length 5, so that's fine. All the arrays that don't match in length, one of the numbers has to be a 1. So what we see here is this is being implicitly converted into something like this. Where I'm adding a 0 to everything on the left-handmost side, and then a 4 to everything on the right-handmost side. Now this works for broadcasting together an array of multiple dimensions against an array that has a smaller number of dimensions. You can also broadcast arrays together when they are each something like one-dimensional or two-dimensional in a way that generates a resulting data structure that has a larger number of dimensions, or we should say a larger number of filled dimensions. So instead of adding my 5x5 array to my 1x5 array, I can do something like this, where I add NumPy to add together. A 5x1 against a 1x5, And the resulting data structure is a two-dimensional data structure of length 5 by 5. Now, because the broadcasting rules, sorry, 1 by 4. This is my 5 by 5. Now, because the broadcasting rules include prepending ones, I don't have to include the explicit reshape call here. So maybe we'll tally this, and we can write this down as a set of rules for doing math, where we say that rule number 1 I guess that's not happening. Where we say that rule number 1 is that the very first thing I have to do is make sure my shapes match. And by match, we mean that one of them can be a scalar, that can be the exact same size and shape, or that they can be broadcastable. Rule number 2, and we've seen this happen quite a bit already, is that my mathematical operations are applied element-wise. So if you are coming from a language like MATLAB and you're used to multiplying two matrices together and getting very explicitly the dot product of those two matrices, this does not happen in NumPy. You'll have to ask for that dot product or that inner product or that outer product very explicitly. The next thing that we're going to have to worry about is what happens when we have special numbers inside of an array somewhere. So what I would like to do next is we are going to take this array A, our 5 by 5, and we're going to coerce it into an array of floating point numbers so that I can insert one of those nan values in it. So to the same name A, we are going to reassign the output of A.asType. We'll make you a 64-bit floating point number array. And let's say in position 2, 3, I want to insert an np.nan. So we've gotten rid of the number 13, and what we have there instead is a missing value. Now the reason that we're doing this is that things that are not a number have special behavior when it comes to performing mathematical or what we haven't talked about yet, reduction operations. And that special behavior is that they propagate. And what I mean by that is that any number added to np.nan is going to return np.nan. So if I have my array A and I try to add 5 to everything, we will see that everything has increased by 5. My 0 has become a 5, my 1 has become a 6. Sorry, I can scroll this up. Except for that not a number in position 13, which remains not a number. Now, this probably makes sense. This might not be surprising, but this behavior, combined with the way that NumPy thinks about reduction operations, might lead to a little bit of confusion. So in NumPy, we have a whole range of functions inside of the NumPy namespace. We've seen one of them already, that will allow us to do things like calculate the sum of an array. And if I do this, we see that the summation for my entire array is not a number. Now, if we think about summation as starting off with a number like 0, and adding in the elements of this array one by one, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2. This is working out really well until we get to this nan. Anything plus nan is nan, and then nan plus 14 is nan plus 15 is nan plus 16 is nan. So these knotted numbers combined with reduction operations often leave you with no data left at all. Now by default, and this is our rule number 4 here, when I apply reduction operations in NumPy, it will take an array and reduce it down to a single scalar value. But this is not always what I want. It's often not what I want. So we have an optional way of specifying which dimension or dimensions we would like to be collapsed by the reducer. So in the summation function, I have an optional second argument. That second argument is axis, and axis accepts an integer value, where that integer value, sorry, I can scroll up. The integer value corresponds to the position in the shape tuple of the dimension I would like to disappear. So in my 5 by 5 array, in the 0th position is the dimension going up and down this way. In the 1th position is the dimension going left to right. So if I want to collapse my data in the left to right direction, I can specify that I want to collapse on the 1th axis. And this value 10 corresponds to the 0 plus 1 plus 2 plus 3 plus 4. 35 to these numbers added together. And here is that nan propagating here. I would love to. Let's do this with a better array though. So I have this array B that instead of being 5 by 5 is 4 by 3. And we can use the difference in those dimensions to make this a little bit easier to think about. So here's my array B. If I look at b.shape, this is my shape tuple. It tells me that the dimension of length 4 is in the 0th position. The dimension of length 3 is in the 1th position inside that tuple. So if I want to collapse the 4 and get a one-dimensional array of length 3, I ask for np.sum of that array B with axis equal to 0. And here's my resulting NumPy array of length 3. Conversely, if I want to maintain the dimension of length 4 and collapse the dimension of length 3, I can collapse across the 1th, or in this case I'll use the negative 1th axis. And now I've gone from a 2-dimensional NumPy array to a 1-dimensional NumPy array, where that 1-dimensional NumPy array is of length 4.
Broadcasting.
Mm-hmm.
Does the array change size? There's a 1 by 5 and a 5 by 1 array. They're broadcasting to get 5 by 5.
Correct. So the question was, in broadcasting, do my arrays change size? The initial arrays do not. So they are not resized or reshaped in any way. But the resulting array can be unexpected isn't quite the right word, but it can have a larger length in each dimension than you might expect if you don't know the broadcasting rules.
So in the broadcasting, they're still doing the referencing.
The question was, in broadcasting, are they still doing the referencing? That depends what you mean by referencing.
So they, instead of changing the original arrays that are used to broadcast, they add a reference which reference to those arrays and then manipulate these.
That's exactly right. So any of those implicit stages in between, where the arrays are getting reshaped during the broadcasting itself, those are not copying any data anywhere. But that resulting array will be a new object. And so we've written on the board here our fourth rule for how math works in NumPy. By default, our reduction operations will collapse everything down to a single scalar value. Now, it might be the case that I'm working with a 3-dimensional or a 4-dimensional NumPy array and I want to collapse 2 or 3 dimensions. And in that case, the axis keyworded argument will accept a tuple of all of the axes you would like to have collapsed. And this is true for most reduction functions, not all. So there are some reducers that will only let you specify that you want everything to be collapsed or only one axis to be collapsed, but not some intermediate fraction. Yes?
Could you help me understand how the word axis is being used?
So the question was, can I help you understand how the word axes is being used? I sure hope so. The axis is corresponding specifically to each dimension. So in your head, if the word axis is confusing because it means other things to you, you can replace that word axis with dimension. I want to collapse dimension -1.
-1 means the last dimension?
Exactly right. So -1 here meaning the last dimension.
So you could replace that with 1 and it would do the same thing?
That's exactly correct. So in this case, it's a little silly. Typing -1 is not significantly more easier than typing 1, but I wanted you to see that this does work. So that if you're dealing with, who knows, maybe a 7-dimensional NumPy array, you might not want to count over, is it the 6th axis or the 7th axis? If you know that you want the last one, you can always just use this -1. Do you have other questions about this? So I have an exercise that I would like you to do. This is going to have you practice the mathematical part. We have separate exercises for the reducers. And we'll spend a little bit of time talking about the different kinds of reductions that we can do as well. It's going to have you practice the mathematical portion of the NumPy stuff. And this is another file we're going to open. It's going to be in a folder called calc under return in a file called calc under return.py. In this particular exercise, you're given a NumPy array. This is just a 1-dimensional NumPy array of stock prices. These stock prices, I believe, are coming from Apple. Your job for this exercise, this is not the hard part. Your job for this exercise is to calculate the return value for the stock for each day using the formula given at the top of the file. So it's today's price minus yesterday's price, quantity divided by yesterday's price. So far this is really straightforward, but here's the catch. I'm not going to let you write a loop. So you have to perform this calculation without using the for keyword or the while keyword. Now, if you're used to thinking about vectorized mathematical operations, this will go pretty quickly. This might take you about 5 minutes. If this is not how you're used to thinking about working with data structures, it might take you a while. There's a trick to it is why. So what I'd like you to do is think real hard about it, and we'll give you about 5 minutes to see if you can come up with a solution on your own. Then we're going to come back together as a class, and I will draw you a hint on the board. So we've all been working on this exercise where we are applying this formula for calculating the return of a stock given some 1-dimensional NumPy array. The first thing that I'm going to do is I'm going to change this formula a little bit. This just makes it easier for me to think about, instead of today's price versus yesterday's, to do today's price versus tomorrow's price. So our new formula is that my return is the price of the stock tomorrow minus the stock price right now divided by the stock price right now. And so conceptually, if I am a person who is standing in location 0 inside of a NumPy array, all of the tomorrows from where I'm standing are offset by 1. So for my NumPy array, I have my prices here. My tomorrows are going to be everything from position 1 onward. These are all of the tomorrow prices that exist. So if I want to know tomorrow's prices minus today's prices, I can take my tomorrow's prices and I could subtract today's prices. When I try to do this, though, I get this error message. It says my operands could not be broadcast together. They have the wrong shape. I would like someone to explain to me what this error message is saying.
Size of the matrix, are they?
Exactly right. So I have two arrays that are almost the same size and shape, but one of them is just one smaller, and it's one smaller because I am very explicitly excluding right now. I'm excluding today. So there are sort of two different ways we can think about solving this. The first is that within the constraints of the NumPy library, I have to have two things that are the same shape. If I do prices 1 colon minus prices 1 colon, I'll just end up with an array filled with zeros, because that's tomorrow's price minus tomorrow's price. So the next thing that I could try, the only option I have left, is to chop off the very last price. So everything up to but not including the last price. And here are the differences in the prices between today's and tomorrow's. Now conceptually what we're doing is if we think about what happens at the very end of my array, so I'm in the last data point, to calculate my return, I need tomorrow's price, but there's no more data left. So I cannot calculate a return for that day. So out of 253, was it? Yeah, out of 253 data points, I can only calculate 252 stock returns. So this is almost all the way there. I need to add one more thing, and that's that division. So I'm going to group my numerator in parentheses to make sure I'm dividing the quantity and not just the last item. And here again, we will divide by our prices from all of the todays. My slash is facing the wrong way. There we go. So this here in 137, this is the solution for this particular exercise. Now, while you were working on it, I went and I coded up a different solution, one that did use a loop. So we can take a look at it really quick. Here's my bad solution. It's a function called bad solution, and it has that for loop where I'm performing that same calculation where the stock return for an individual day is tomorrow minus today divided by today. And this will give us the same answer, but I'd like to ask something a little bit different. I'd like to ask which one of these is more performant. So just like before, we can use that magic time it function. And here we can apply it directly to this expression using NumPy's vectorized math. And it tells us that it can calculate the returns for my 250 stock prices in about 2.2 microseconds. I will do another magic time it, this time calling that bad solution function on those same prices. We are now at 104 microseconds, so this is 50 times slower. And again, typically the difference in the running time for each one of these solutions is going to grow as my data get larger as well. In this particular case, there is still a for loop happening somewhere. But when we use vectorized strategies like this, where I'm creating not new data, but references to just one set of data somewhere, and I'm letting NumPy vectorize the mathematical operations between the eventual references, those eventual values. All of that looping happens way, way down low at the level of C. And when I have that looping very up high at the level I am in Python, it's going to be a lot slower. So even though in the solution we're still using, in my bad solution, this is still NumPy subtraction, so I'm still taking advantage of that static typing. Specifically because I have that Python for loop in the way, I'm getting a greatly diminished performance. So this is one of the common pain points in your code if you're doing a lot of math in NumPy, but it's inside of Python loops. There might be a way to vectorize that using references to the NumPy arrays themselves. We have time in here to do one more big exercise. Before we can do that, though, we're going to have a brief tour of the reduction operations that are available to us inside of NumPy. So we've seen sum a whole bunch already. That was np.sum. We also have other reduction functions to calculate statistical properties of arrays. So for example, I could ask for the np.mean of my prices. And just like sum, I can ask for the mean across just one particular axis. In this case, prices is a one-dimensional data structure, so having an axis here wouldn't make sense. So I can ask for the mean of my prices, and I have that same standard deviation, and also variance. I might want to know the minimum or the maximum values, and I can find this using np.max of prices. So the maximum stock price for Apple in 2008 was $194, I'm assuming that's dollars. I can also ask for the minimum. The minimum price was $80.50. Now, for some of these reducers, I have sort of friendly methods that instead of telling you what the minimum or the maximum value is, will tell you where it occurs. So if I wanted to know the integer location of the lowest price, instead of asking for the min, I can ask for the argmin. And it tells us that this minimum price occurs 225 days into the year 2008. Similarly, I can also ask for the argmax. And it tells us that the maximum stock price was on the very first day. So a lot of movement downhill for Apple in 2008. Now there's one thing to be aware of when I'm using things like argmin and argmax. And that has to apply to NumPy arrays that have multiple dimensions. So if we pull up, let's pull up B, our two-dimensional NumPy array. So this is my 4x3 array. And what I would like to do is I would like to ask where the np numpy.argmax is of my array B. So I'm calling the np.argmax function on B, and I don't get this information back in 2 dimensions. So it's not telling me that it is in position 3, 2. It tells me it's in position 11. So when you use functions like argmax and argmin, the first thing that NumPy does is it flattens it out into a one-dimensional NumPy array. This is usually not the actual number you want to end up working with. There are a couple of ways that you can turn this 11 back into an index that knows about 2 dimensions. The easiest is to use a function defined inside of NumPy called unravelIndex. So if ravel is a way of flattening an index, unravel is a way of unflattening the index. UnravelIndex is going to take some integer like 11, and the shape I would like it to be unraveled into. So in this case, it'll be the shape of the original array B. So putting this all together, we can ask NumPy to .unravel my index. The index I want to unravel is the output of calling np.argmax on B. And this gives me my raveled, my flattened index location. And then finally, I'm going to give it b.shape. For the shape of the two-dimensional data structure, I would like you to be unraveled into. And what this returns to us is the tuple 3, 2, which you should be able to convince yourselves is the two-dimensional location of the value 11. So the last exercise we'll be working on in here today is going to have you use, it's going to have you practice these reducers on a series of NumPy arrays. So this will be in another Python file inside of another exercise folder. This one is going to be called wind statistics. And in win under statistics is a file called win under statistics.py. It's going to have you read in some win data where the first three, I don't want to call them columns, but the first three data points are representations of the year, the month, and the day as numerical integers. And the rest are wind speeds recorded across a bunch of different stations inside of Ireland. And you're going to practice finding things like the minimum, the mean, the maximum. You're going to do it for all the locations. You're going to do it for each location. There are some, I don't think they're marked as bonus. Oh, maybe they are marked as bonus. There are some bonus questions at the end. I don't expect we'll have time to get to those today. And dear Pythonistas, it is now 12 o'clock. This marks the end of our tutorial session. I don't want you, however, to take this as a signal that you're being forced to leave the room. I'd like you to see it as an invitation to linger. So maybe there's something we talked about during the tutorial today that you're still a little unsure of. Maybe you have a question about the broader Python ecosystem that you felt was inappropriate to bring up during a class specifically on NumPy. Maybe you've been really aching to sing a song to Alex, but you didn't want to interrupt. I would like you to see this as an opportunity for all those things, to come up to bring your questions to us, to bring your concerns to us. For those of you who are heading off to lunch, I would like to wish you an enjoyable rest of the conference. Thank you so much for your attention.